All right, so the plan today is just to continue with differential equations. We covered separable equations last class, um, and first order linear, and a couple of examples, a couple of applications from separable equations are available on the YouTube channel and the supplemental materials folder or playlist. So that's kind of the next topic after separable equations and first order equations. And remember, the goal of both of these was to generate algebraic solutions to the equations, to the differential equations. Today, the goal is to talk about direction fields. I mentioned briefly last time that this is really a directly geometric approach to getting graphs of solutions. And then we're doing pretty good as far as timing is concerned. So we have a kind of makeup review day scheduled for next class, I think. So we'll use that to talk about the basics of second order differential equations. And as I mentioned, diffeq is a huge topic. We're kind of really only scratching the surface, even though we're devoting 3 or 4 class meetings to it, we're still only scratching the surface of this field. So if you enjoy this material, we offer a full course differential equations that you might be interested in. Some other administrative notes, lots of stuff to talk about today. All of the differential equations homeworks are posted, so the material from first order as well as some selections from chapter 17. We're of course not covering all of chapter 17, just kind of touching on second order differential equations. There are some bonus problems. So the bonus problems will look like they have a point value of 0, but then when you complete them, you get bonus points added on for the different parts. So when it says like, at the scroll bar across the top, it might say like, out of 6, like dash out of 6 or 4 out of 6 or something like that. When you start that problem, for a bonus problem, it'll say out of 0, like dash slash 0. And if do it and get a couple points, it'll say like something like 3 out of 0. So you're you're not getting an infinite homework grade if you complete one one point and get 1 out of 0. It's just that 1 is being added to the numerator and 0 added to the denominator of the calculation. So particularly in the direction fields section, there at the very end, there are a couple of Euler's method problems. If you're interested, you can look up Euler's method, and I might go and grab a lecture from one of my previous differential equations classes and pop that into the supplemental folder as well if I can find one easily enough. But Euler's method is basically just a numerical version of direction fields. So it does numerically what direction fields do graphically. And then there's a pendulum problem at the end of the second order differential equations that is also a bonus problem. I think those are the only bonus problems. There might be another one in there somewhere. But I do tend to put the bonus problems at the end of the assignment. So if you ever see that, dash slash 0, like out of 0 points, those are bonus problems. And then next week we have the midterm exam coming up. It will be taken on WebAssign essentially at your leisure. So it's not tied down to class time. Just works a little better to do it that way in a remote course. So since it would have to be on some kind of online system anyway, giving you the flexibility just makes sense, I think. So it'll be available from 9 a.m. on Monday 3:10 through 11:59 p.m. on Sunday 3:16. The material will be chapters 6 through 9, what we've covered in 6 through 9, and implicitly, of course, 1 through 5 as well, right? So you might need to do a substitution to complete an integral. Well, that's a chapter 5 topic, but of course we're in Calc 2, we're assuming Calc 1 material at this point. So if you're developing a review plan, it's probably a good idea to review a bit of the last half of chapter 5. And if there's anything else that you noticed, maybe like antiderivatives for trig functions are kind of difficult for you, well, maybe then going back to the Calc 1 material and looking at derivatives of trig functions, that might be another way to kind of tackle that. So just keep that in mind as well, that sometimes reviewing some of that prerequisite material can really help with the current material. The sample exam. So I'll post the sample exam later this week, probably tomorrow or Wednesday. And that'll be very similar to the actual exam, similar types of problems, um, same number of problems, similar length of the exam. So that'll be posted later this week. And I usually recommend using the sample exam as an assessment of your current knowledge rather than using it to kind of directly study for the exam. So some students will look at a sample exam and they'll kind of look at problem one and think, okay, I'm not 100% sure how to do that. Let me like break out the book and my notes and kind of work through problem one on the sample exam. Okay, I got the check mark. Now I got a problem two. I recommend not using it that way for the same reason that I recommend not doing the homework that way. Um, and that's that you're only really going to learn that material to kind of the lowest bar necessary to get that check mark. So the actual exam, the question's going to look a little different, and then it's going to be kind of almost back to square one. But what I would recommend is when you feel that you're prepared for the exam, uh, take the sample exam as though it were the actual exam. So time yourself. I haven't decided on the time limit yet or haven't set the exam yet. So all of this is still a bit up in the air. But when I tell you what the time limit will be for the actual exam and for the sample exam, time yourself in the sample exam. Go through, when you feel prepared for the exam, go through the sample exam, take it as if it were the actual exam, turn off the TV, find a quiet environment where you can focus and so on. Put your book and notes and so on away, and then go through the sample exam as if it were the real exam. If there's a problem that just like took you a really long time to do, you made a couple mistakes, or if there were problems that you got wrong, at the end, take a look back at those topics, use those to guide your study and say, okay, I want to spend a little more time reviewing these topics, and maybe the ones that you kind of breeze through, maybe spend a little less time reviewing those topics. Or if at the end, if you ran out of time, I try to make my exam so that time is not a really important factor. But that being said, there is a time limit for the exam. So if you ran out of time at the end, maybe ask yourself, what are some efficiencies you can come up with? Um, is it just doing the algebra that's taking a long time? Or, if you're a little quicker with the strategy, if you're a little quicker at recognizing, okay, this integral, I'm probably going to want to use this strategy, this integration technique for it. Um, if you went down a couple of kind of blind ends before, or dead ends before coming up to the right strategy, maybe that's something that just with a little more practice, a little more pattern recognition, you can do a little more quickly. As I mentioned, no Proctor U on the exams just because of the technical issues we've been having. It is on WebAssign, so you'll log into the exam. You'll take it the same way that you'll take the sample exam. It'll feel very similar to like a homework. It's the same system that you interact with, the same method of entry and all of that as any of the homework problems. The problems that I put on the exam are from the same pool that could be put on the homework set. So it should feel very similar to a homework, just a bit lengthier and timed, of course. And then just a very strong caution to not wait until the last minute to take the exam. I would recommend planning to take it on or before Thursday night, Thursday of next week, of course. So giving you a good heads up here. So next week is the exam. Plan to take it on or before Thursday night. That way, if anything goes wrong, technological issue, power outage, something like that, whatever it may be, that gives you a lot of flexibility. You can come to a CCAC campus if you need to, go to a local library. You can try to get the text sorted out. You can get in contact with me. If you wait until, Saturday or Sunday to complete it, your options are going to very quickly reduce the closer you get to the due date and time. All right, so there's quite a bit of administrative stuff, but I think it is important to just have all of that out there. Our quote of the day is a little more of an idea of the day from philosopher David Hume. So he lived in the 1700s or so. And kind of one of his ideas is what's sometimes referred to as Hume's guillotine, kind of like slicing in two, two different ideas that we can't derive ought statements, so statements of kind of morality or what we should do, from is statements, from factual statements about the way the world works, right? So we might have a law of gravity that says how gravity works, but that doesn't really inform what we should do with that piece of information or should do in light of that piece of information. Science as a field, and I kind of, loop mathematics, applied mathematics kind of loosely in with that. So things like statistics or like what we're doing here, modeling with differential equations. Uh, it's quite good at is statements. It's quite good at discovering new things about the way that the world works and making factual statements about the world and even the ability to predict what will happen under a set of circumstances. Uh, but we shouldn't we should stay in our lane as scientists. We shouldn't say because science says that this is true, that means we ought to do this other thing. The ought statement, the statement of morality brings in a lot of ideas about values, about trade-offs, right? And maybe ideally this thing would be nice to do, but there's a large trade-off for that. What trade-offs are we comfortable making? What are our value systems that we're working with? What are the cultural norms and all of that kind of come into the ought side of things. So that's Hume's guillotine. Uh, let's keep science on science's side, where it's very good at telling us how things work. And let's appreciate that morality is something different, where we're kind of deciding, in a sense, what are the terminal goals? What are our just things that we want to happen because we want those things to happen, right? Like I like chocolate cake because I like chocolate cake. Uh, but then the question of like, how do I get a chocolate cake? Well, I have to get in the car and drive to the store and, uh, I would say get the ingredients and bake it, but you probably would not want a chocolate cake baked by me, but go to the store and buy a chocolate cake or something, right? Science can tell us all of those procedures to get the chocolate cake, but it can't tell us that I should buy a chocolate cake instead of a strawberry cake or something like that. All right, so that is the thought for today, as well as all of our administrative background. Okay, so just a really quick, because it has been 5 days since our last meeting, just a really quick rehashing here. Recall that in differential equations, we use our famous y prime equals y as an example. Our solutions are functions, something like, say, y equals ae to the x, and in particular, there are families of functions. So I can look at the graph of such a function for different values of a. So I might have, a equals +1, +2, -1, -2, even a equals 0, which I'll draw in green here for no particular reason other than I already drew my axis in black, so this makes it stand out a little bit. But I can represent a function or a family of functions graphically like this. And then, of course, I can pluck out a certain function, y equals 3e to the x or something, and construct a table of values. That would be another way to represent such a function. And this is what Euler's does. If I have the algebraic solution, I can kind of just pretty easily get the graphical and the tabular solution most of the time. But what the direction field looks at is it looks directly at the geometry of the differential equation itself. So starting here, not working off of the algebraic solution, starts directly with the differential equation and directly attempts to get a graphical representation of the solution. So it's a direct technique for finding approximately graphical representations of solutions. Now, why would we want to do this? Well, I mean, I guess if we have the algebraic solution, we probably would just use that to kind of to inform our understanding. But maybe we have a differential equation where it's really difficult, or maybe even essentially impossible, to get an algebraic representation of the solution in a nice form, right? Sometimes we can get away with something like maybe an infinite series, but that's not a super helpful version of an algebraic solution all the time for all aspects. Okay, so we're looking directly at the geometry of the differential equation, and we're considering a first order differential equation where we have y prime equals f of xy. And if we ask ourselves, so equation one here, dy dx equals f of xy, what does this really say? Well, I have a coordinate plane, xy. It tells me at some point xy, maybe this point, x comma y. At that point, I can evaluate f there. What's f of xy? Maybe it's, say, positive 1. It tells me that if I have a solution going through that point, it's got to have slope positive 1, right? Maybe f of xy equals positive 1 for this choice of x and y. And that's the kind of locally the slope there. It's kind of the first order approximation to whatever the curve would look like going through that point. Maybe at a different point, maybe over here, I have a different value of x, different value of y. I plug those into little f. Maybe I get 1/2. So at that point, x comma y, dy dx is 1/2. It's a less steep slope. Again, first order approximation there. Or maybe at a third point, I don't know, say down here, for this value of x, this value of y, maybe when I plug into f, I get -2. I get a steep negative slope. Again, kind of as a first order approximation near this point. If if a solution curve goes through here, it'll have to have that slope -2 right at the point, and it'll kind of follow this line with slope -2 going through this point more or less closely when my solution curve is near this point. Okay, so let's look at an example here. Actually, before we kind of jump right into the graphical side of things, we're going to just use these ideas, use the kind of geometric ideas to answer some what are kind of more algebraic feeling questions first. And this will actually help us with our graph as well. So let's take a look at a population dynamics model. The most popular model is the so-called Malthusian growth model, something like y prime equals y, or maybe y prime equals ky, just an exponential growth model. It kind of has a shortcoming though. It predicts that if y equals a e to the t, let's put t there for time, it kind of predicts that population grows unbounded over time. So if I wait long enough, the Earth will have, 300 trillion people on it or something. Well, of course, it's not going to be able to sustain that. So we could look at a model like this one called the logistic model. And the number 2 in there is just there as a number. If we wanted to put a parameter in there, we could put a k there. But dp dt equals, in this case, 2 times p times 1 minus p. Again, remember that p is our dependent variable here, and t is our independent variable. So the growth rate depends only on the dependent variable, not on the independent variable. The slope is independent of t. We call this an autonomous equation. Autonomous meaning, like, roughly speaking, self-referencing, self-named. So auto means self, and nomos referring to name. So the right side, p, only contains, or sorry, the right side only contains p. It only contains the dependent variable, 2p, 1 minus p. So to know how fast the population is increasing, all we need to know is the population value right now. We don't need to know what time it is right now, how much time has elapsed in this scenario. So we could ask questions like, well, one of the slopes positive, negative, or zero. I know that P prime is my slope. I can actually plot P prime as a function of P. Very importantly, this is not a solution that I'm plotting here. This is not a direction field. This is not a solution. This is just a little schematic that I'm drawing to help myself. So I want to be very clear about that. We're not plotting the solution here. We're not drawing a direction field. I'm just plotting P prime as a function of P. Because this is an autonomous equation, I can do that. And I see that when P is 0, the slope will be 0. So of course, the origin there. And I also see that when P is 1, the slope will also be 0. I see this as in terms of P, is a quadratic opening down, has a negative 2P squared as its quadratic term. And I note that P prime, my slope, will be positive when P is between 0 and 1. It'll be negative when P is less than 0, and it'll be negative again when P is bigger than 1. And it'll be 0 when the population is either 0. Of course, if there's nobody in the population doesn't grow at all. That kind of makes sense. That also made sense for our Malthusian model up here. This y equals 0 solution was when we started with no population and we don't spontaneously get population. But we actually have another, what we might call an equilibrium solution. The slope is 0 again when P is 1. So my slopes are 0 when P is 1, positive when P is between 0 and 1, and negative essentially otherwise. P less than 0 or P bigger than 1. So where are the equilibria? Well, if I'm at P equals 0, then P prime equals 0, which means I don't change from there, right? If I'm at P equals 0 times 0, P prime is 0. So then at time 1 or 0.1 or 0.01, whatever my next increment in time would be, I would estimate the population still to be 0. And then when I move forward that time step, P is 0, P prime is still 0. I estimate the change in population to be 0 over the next little time interval. I do this again and again. No change. These are equilibria. Or I can see explicitly that P of t equals 0. dp dt is 0. My left-hand side and my right-hand side are both 0. I can see explicitly that this is an algebraic solution. I can just verify that by plugging in. But also P equals 1. If P of t is 1 for all t, then dp dt is 0. And 2 times 2 times 0 is also 0. This also is an algebraic solution. So we can say the same here. There are two equilibria in this model. Let's come back to the question of stability. We'll think of that in just a second. Can solution curves cross each other? That's another kind of interesting question. So let's do stability before we move on to that, I think, while I have this on the screen. Okay, let's revisit our little not solution graph up here. This is not graphing P as a function of T. It's just graphing the relationship between P and P prime. So what happens to P locally whenever P prime is positive? When my slope is positive, if I was like in this kind of scenario here, the slope is positive. Well, my value of the dependent variable is increasing. So in the regime where the slope where p prime is positive, that means p is increasing. That means we're heading this direction on the interval 0 to 1. Right? That means we're heading in the direction of larger p. We're heading to the right. So if I had p equals a half or p equals 3/4, my population is growing. It's getting larger over time. What about when p prime is negative? That means my population is shrinking over time. That means my change in population is negative. My population is getting smaller. So if I was down here at, now this doesn't make a lot of sense from a population growth model, but mathematically we could be negative. We could have negative p, and it will be heading in the negative direction. So if p was at like negative a half, p prime would be negative there. We'd be getting smaller. We'd be going further towards the left. But also if p was out here at like 1.5 or 2, p prime will be negative. My population out here to the right will be getting smaller. I notice for my two equilibrium points, maybe I'll highlight them in red here. For my two equilibrium points here, 0 and 1, they have kind of different behavior, right? If I am smack dab at p equals 0, p prime equals 0, and we don't get any change. What if I deviate even a tiny bit from there? If I deviate even a little bit to the right, then p is bigger than 0, p prime is positive. Over time, p is going to keep growing. It's going to move further away from 0 to the right. Or if I deviate a little bit to the left of p equals 0, p prime is going to be negative then. That's going to make p even more negative, which is going to make p prime even more negative, which is going to make p even more negative, and p prime even more negative still. We're going to keep going to the left. We see that 0 is unstable. If I'm smack dab at p equals 0 perfectly, I just stay there forever. But if I deviate even a little bit to the left, I keep going to the left forever. And if I deviate a little bit to the right, I at least locally keep shooting off to the right. It's a little bit like being at the top of a hill and balancing a ball there. If you get it just right, it'll stay there. But you knock it a little bit one way or the other, it's going to roll down. Right? You knock it a tiny bit to the right, there's a little bit of a slope there, so it picks up a little bit of speed, goes a little further to the right where there's a steeper slope, picks up more speed, goes further to the right, and so on. So this like positive feedback. On the other hand, if we look at p equals 1, if I deviate to the right a little bit, well, when I'm to the right of 1, I'm getting pushed back to the left. If I deviate to the right a little bit, I get pushed back towards 1. Or if I deviate to the left a little bit, that positive slope then is pushing me back towards 1 again. This is like kind of being in a valley, right? If I kick my soccer ball, it just kind of comes back towards equilibrium. Of course, so long as I don't kick it so hard that it goes over a hill or something. But locally speaking, if I deviate a little bit, I just kind of come back to that equilibrium. So p equals 1 is actually stable. Can solution curves cross each other? If I think of these solution curves up here, I've drawn them so that they don't cross each other, but and in this particular example, it seems like they can't, but can they never cross each other? And the kind of short answer is kind of roughly speaking, under pretty reasonable conditions, solution curves cannot cross each other. What would it look like if they did? What would it look like if I had a solution curve like this that came in and crossed another solution curve at a point? We know that the way that we decide which one of these solution curves we are interested in following is based on initial values, right? Initial conditions. We had an initial value problem. We couple a differential equation with maybe something like y of 0 equals 5. And that plucks out a single one of these members of these families of functions. If I want my initial value problem to have a unique solution, well, what would it mean if I had this differential equation and chose that point as my starting point, the point of intersection of two curves? That would mean that I could either follow this trajectory or follow that trajectory. I don't have a unique solution anymore. I don't have a well-defined problem. I have a problem with at least two solutions now. And that's no good. Now, again, we talk a lot more about the details of this stuff in a full differential equations class. So, I mean, what I'm giving you here is in no way any kind of a mathematical proof or even really a strong argument for why this kind of a setup should be well defined and should have a unique solution or when it should. But I'm just kind of arguing heuristically. We know that we want to use these models, practically speaking. We know that we use them to model things like pendulums and mass spring systems and population growth and so on. And it'll be kind of silly to use models where, I plug in all my inputs into the model and it says you might follow one of these 20 paths, that wouldn't be a super useful physical model. So kind of why? The precise answer is quite complicated. The practical answer is our initial value problem starting at that point of intersection would have multiple correct answers, multiple correct paths forward. That's kind of a silly model. We would like our models to tell us what will happen, not, maybe one of these 20 things will happen, right? If I pull a pendulum up and let the ball go, I want it to say this is what the function is going to look like as a function of time, not, it might be one of these 12 functions. Okay, so now with this kind of understanding, looking at where are the slopes positive or negative, where are the equilibria, what kind of equilibria are they, let's try to draw a few representative solution curves, and then let's try to use technology to draw a direction field. Okay. So just a reminder, P prime is 2P 1 minus P. And now we're drawing things that do look like solutions. Again, remember this little picture up here, this quadratic thing was not a solution. It was just helping us understand what's happening to P in different regimes when P is between 0 and 1 or less than 0, bigger than 1. Here's where we're actually transitioning to drawing solutions that look like P is a function of T. Okay. Now, one thing that I notice is that when T is 0 and P is 0, at this point, if I have a solution curve that goes through there, P prime has to be 0. So if I draw a little chunk of a linear approximation at 0, 0, it should be a flat line like that. So this might be at P equals 0, T equals 0. If I was to look at P equals 0, T equals 1, I would actually have the same thing, right? That's what it means to be an autonomous equation. When I move along in T, there's no explicit dependence on T here on the right side of the equation. So my slope only depends on the value of P. If T equals 1 and P equals 0, P is still 0, I get the same tangent, same horizontal tangent at 2 or 3, and so on. So in other words, if I have a solution that goes through 0, 0, locally, near 0, 0, it should look like the horizontal line, P equals 0. It should just follow this curve out a little bit to the right. Maybe I'll actually draw that in red because it'll show up a little better. I'll follow this curve out to the right. and I run into, say, 1 comma 0. Now, if 1 comma 0 had a slope like +1 or something, then I would start following this slope instead, but it doesn't. It has a slope 0, which tells me keep going to the right. 2 comma 0 has slope 0, which tells me keep going straight to the right. This is my equilibrium solution, p equals 0. I have a similar one of these at p equals 1, another equilibrium solution. When p equals 1 and t equals 0, say, p prime is 0 here, my linear approximation near 0 comma 1 is just going to be this horizontal line, this in this case p equals 1 near 0 1. But the same will be true at, say, 1 1 or at 2 1 or at 3 1, and we'll do the same kind of thing. We'll just follow these lines here, and this is our p equals 1 equilibrium solution. And by our kind of not very good argument back here, can the solutions cross each other? No. Any of our other solutions should not cross either of these equilibrium solutions. These two red lines, p equals 0, p equals 1, are legitimately solutions to our differential equation. None of our other solutions we're going to draw in should cross either of these. Now I look at something like p equals 1/2 and say t equals 0. So when p equals 1/2, p prime is 2 times 1/2, or that's 1, times 1 minus 1/2 is plus 1/2. So this has a slope of plus 1/2. But actually the same is true for the local slope near 1 comma 1/2 or 2 comma 1/2 or 3 comma 1/2. With an autonomous equation, when I get kind of one column of these directions or these slopes, I can just copy them over to the right. I see that if p equals, say, 3/4, p prime is going to be what? Well, it's 3/2 times 1/4. That's 3/8. It's a little shallower than 1/2. It's a little less steep. So that's 3/4. Or actually down here at 1/4, when p equals 1/4, I'll actually get the same thing. Because 1 minus 1/4 is 3/4. So I still get 3/4 times 1/4 times 2. A little shallower. If p is below 1, but pretty close to 1, if p is near 1, 2p is near 2, but then 1 minus p is quite a small number. It's a number close to 0. So up here, I should have a very shallow, still slightly positive slope, but very shallow slope. And same thing if I was close to 0 on p, I'd have 2 times a number close to 1 would be about 2, but then times something quite close to 0 is also close to 0. Very slightly positive slope, but close to 0. And now I can kind of imagine that what I'm looking at here is going left to right, like a river flowing along. And each of these little lines represents kind of, if I stuck my finger in the river at that point, where I'd feel the force of the water going. And I imagine I put a ping pong ball, say, right here, and I just let the ping pong ball go where the flow takes it. It's a bad start. There we go. Maybe something like this. I know it's going to not cross. It's not going to cross the red curve, but it's going to keep getting closer. It looks like it's going to asymptotically approach that red curve. If I'm down here, I start almost horizontal, but my curves start getting steeper and steeper until I get pushed up towards that p equals 1 curve, and then I flatten out. Start quite close to 0. It might take me a while. And remember, these solution curves shouldn't cross each other either. So they're all kind of lined up really nicely, these little almost like hysteresis curve looking things. And I can't really draw those much further without uh, crossing them over just due to my lack of artistic ability, but you can imagine we have a bunch of these curves kind of scrunching up near the p=1 as we go further to the right. Now, similarly, if p is bigger than 1, then we know the slopes are negative. If p is a little bigger than 1, the slope will be a little bit negative. It's an autonomous equation, so I can just kind of copy my work left to right. And I can see that solutions that start up here decay to p=1. Looks almost like an exponential decay up here. We see this as a stable equilibrium because if I'm at 1, I stay exactly at 1 forever. If I go up a little bit, I decay back to 1. If I go down a little bit, I increase back to 1. This is like population growth with a limit, right? If my population gets a little too big and I don't have the resources to support it, the population dies off until it's at a supportable level at 100%. If I have a disease or something that kills off 10% of my population, it goes down, but the resources are still there to support the population. Populations tend to increase over time. It'll increase back up until the resources are fully accounted for. If I'm at 0 population, I don't go anywhere. But if I'm at a lower level of population, the impact of this cap is that I don't get a solution that just grows with exponentially without bound. That's maybe a bad model in some sense. I get solutions that kind of grow somewhat exponentially, right? This looks like kind of exponential growth, but then it starts to kind of tail off as we start using more and more of a percentage of the resources available to us. So one way to look at this is use of resources. Another way to look at it is this p squared term is like an interaction term. So maybe the more that individuals interact with one another, they're competing for different things, resources or mates or whatever it may be, they actually might, harm each other or kill each other. So that's another way to kind of look at that interaction term. And then, of course, doesn't really make sense in the population model context, but mathematically speaking, we could allow p to be negative. When p is a little bit negative, my slope is a little bit negative. When p is more negative, my slope is more negative. And we see these curves look like exponential growth kind of in the negative direction away from 0. So we see that 0 is an unstable equilibrium. If I move a little bit up from 0, I'm going to get attracted to p=1 to that equilibrium. If I move a little bit down from 0, it doesn't make sense in the population, but if I imagine doing that, move a little bit down from 0, I shoot off to negative infinity. The only way I can stay near 0 over time is to be exactly at 0. But if I start out near 1, even kind of far away from 1, as long as not too far, then I get sucked into 1. 1 is a stable equilibrium. It sucks solutions into it. 0 is unstable. It pushes solutions away from it unless they happen to be exactly at 0. So this would be a direction field. All these little lines, these little green and blue and red little line segments that I drew, representing little linear approximations of solutions if they go through that point. And then all of these black curves that I've drawn here would be estimates or graphical representations of solution curves, solution functions. So I've drawn here a representative sample of the family of functions that are solutions to this differential equations, and I've done it directly geometrically. We've done essentially no algebraic solving of this differential equation, right? We have no idea what the solution of this looks like. The only algebra in a sense we've done is like kind of the simple algebra to figure out, uh, you know, where's p increasing or decreasing, things like that. So that's not the algebra I'm talking about. I'm talking about we haven't done, solve this as a separable equation or a first order linear or anything like that. We haven't gotten p prime equals function of t anywhere, but we have a pretty good idea of what the solution to this looks like and how it behaves. There are equilibrium solutions. I'm kind of tending to head towards one and away from zero, things like that. I can get a lot of understanding about a differential equation by looking at the direction field. Okay, let me pull up a website here. I'm going to pop the website into chat. There are several of these online. I like this one. I think this, there, I popped the website into chat. Oh, let me switch my share as well. There we go. There are a few sites like this. This one I like because it is very similar to a program called JODE up here that I think you can still download. It's a little harder to find now, but it's an old like Java or JavaScript or something program, probably Java. And this one's very similar to it, this website. So I like this one. And here we're just going to enter this differential equation. So we have dy dt. So we need to rephrase things in terms of y is the dependent variable and t is the independent. So we just have to be a little careful with that. So I need 2 times my dependent variable over on the right is p. So now it's y times parentheses 1 minus y. We do need to explicitly put in things like times and things like that. And we can set our min and max for t for a window going left to right, or for y or p going up and down. Let's let y go from maybe -1 to +2. Vertically, we go -1 to +2. That should get us a nice picture, I think. And t, let's go from 0. Let's go to 5. That sounds good. Arrow length, let's just see how that looks. Number of arrows, 20. Hopefully that'll look pretty good. We'll try it. And let's leave all of these as they are. And I click graph phase plane. These direction fields, slope fields, sometimes they call them phase planes or phase portraits. And I see something very similar to what I see over here. I don't see the exact 0 and 1 equilibrium. Maybe if I change my number of arrows to like 21, will that help? That made it worse. Let's try 19. I don't want to think too hard. All right, well, I'm not really having too much luck here getting those exact zeros and ones to show up. But we can see that we get a very similar set of direction lines as over here. But the other thing we can do, the other thing I really like about this one is we can just click on the graph and it'll enter. You can see up here where it says initial t and y. It'll just pick that point and it'll say, what would an initial value problem going with this differential equation going through that point, what would the trace of its solution look like? It would look like that. I can just pick an assortment of points just to kind of fill in my set of solutions here. And it's very easy to do with technology. And I can see if I want to hard code in t equals 0, y equals 0, fingers crossed that this traces a nice horizontal path. Yeah, that did work pretty well. And the same with t equals 0 and say y equals 1, we see that equilibrium solution as well. Every once in a while with some of these equilibrium solutions where they're unstable, just because of the way the computer does the approximation for things like this, sometimes they don't quite look like equilibrium solutions. That just has to do with the fact that we're approximating solutions. These aren't exact solutions that we're looking at here. But in this case, it actually worked out pretty nicely. Okay. So let's take a look at an example like this, growth with harvesting. Here, P prime equals Kp. This is like the Malthusian model, but then minus R. Here we're going to focus on, let me switch back to just OneNote. Here we're going to focus on drawing this by hand because, well, I have K and R here as parameters. I can't really get a good feel on how they interact if I just pick numbers for K and R and plug it into the plotter over there. So when I have parameters like this and I want to understand how they interact with the solutions, it's going to be better to do some work by hand. So again, I'm going to look at P prime as a function of P again, not a solution here. We're just drawing a little diagram to help us figure out when things are going to be increasing or decreasing in what regimes. This is autonomous. The PDT only depends on P, not explicitly on T. I see that when P is what? R over K, that's when I have an equilibrium solution. P prime equals 0. When P equals 0, P prime is negative R. Extend this down a little bit. When P is 0, P prime is negative R, and I know that this is linear. So I see that P is increasing when P is greater than R over K and decreasing when it's less than R over K. So here's T, here's P, these are solutions. Now, so this is not a solution, it's just helping us understand the regimes when P is increasing or decreasing. And I see at R over K, we're taking R and K both to be positive here. I have an equilibrium solution. If I choose my harvesting rate R to mesh with K in just this way, then I have an equilibrium solution. If, let me pick a different color there. If P is less than R over K, if we're on this side, P prime is negative. If it's a little less, we get slightly negative slopes. If it's a lot less, we get more negative slopes. So we have this kind of exponential growth away from our equilibrium, and our population goes to 0. If we harvest too aggressively, our population dies out. And vice versa, if P is bigger than R over K, P prime is positive. It's a little bit positive if P is a little bigger, and a lot positive if it's a lot bigger. This is autonomous, so I'll just copy my lines over left to right, and I see I get exponential growth away from that equilibrium going up. If I don't harvest aggressively enough, my population explodes, gets larger and larger. So I could get uh, a really good idea of what's going on here kind of qualitatively just by looking at this picture and at this picture, even though it's not a solution, it helps us understand what's going on. Again, note that nowhere have I written P of t equals some function of t. We haven't done anything as far as the algebraic solution is concerned. We directly are looking at the geometry of the differential equation here. Okay, and then let's pop back over to the technology to help us with this one. So we can talk about finding these by hand, but it's a bit of a pain. So we can find things like isoclines or nullclines. The null lines are all of the places where the derivative is, where the slope is 0. In an autonomous equation, that meant equilibrium solutions. But in an equation like this, where we see explicit dependence on the independent variable, that's not necessarily the case. Or we can look at isoclines. We can set y prime equals c. We can find what curve in 2 dimensions is, for what curve is it true that, say, along that curve, the slopes of this direction field is always 1, or is always 2, or is always 1/2, or is always -1. So those are isoclines. But for something like this, we would probably come over to technology and ask it to graph it for us. Actually, not sure how to have it clear, so I just reloaded the page. And here I have y is the dependent variable, x is the independent variable, so I need to switch that to t. So I need t squared plus y squared minus 1 for my dy dt. And we see that when x and y are both 0 at the origin, y prime is -1, the slope is -1. That seems like a pretty reasonable slope. Let's keep our window on -5 to 5 on both axes. That seems like a pretty good first guess. And something that I kind of see here is if I look at all of the lines where I have, like, say, slightly positive slope, they kind of like go around in a circle, right? If I look at, like, when is y prime equal, um, say 2 or something, or let's say 1. When is y prime equal 1? That's when x squared plus y squared minus 1 equals 1, or when x squared plus y squared equals 2. That's just the circle of radius root 2. I can see on the left here, I have solutions that pretty much just go straight up, and same off to the right. But when I start getting into this kind of circle where things are getting, like, twisted a little bit, I actually get pulled into the circle sometimes. I actually go from having no local extrema to having a local max and a local min. And sometimes I kind of get, like, sucked in by the influence of the circle, but don't quite get pulled down. So, maybe there's an extreme here where I would have one horizontal tangent, like kind of a y equals x cubed kind of deal, where it's not a local max or a local min, just one horizontal tangent. Or sometimes I'll have two. So that's what the direction field would look like for this one. And then we're about out of time, but if you want a little bit of practice, you could use technology like this to draw direction fields, or slope fields, or phase planes that go by a lot of different names for these two examples. All right, y prime equals negative y squared over x squared, or y prime equals sine of x minus y. And before you draw them with the technology, give a little bit of thought to, like, heuristically, qualitatively, what do you expect from these direction fields? And then does what you get from the technology match what you predicted? Okay,